In our last video, we talked about liquid manometers. We use them a lot for pressure measurement. Today, we'll talk about differential liquid manometers. They're used to measure the pressure difference between 2 points. Let's start with this example. A differential manometer shows this initial configuration. Then, it's linked to the points A and B as shown. Now the configuration turns to this. The pipes are filled with oil, whose specific weight is 8,000 newtons per cubic meter. We know that pressures at A and B are 200 kilopascals and 193.4 kilopascals, respectively. Find the specific weights of liquids 1 and 2. Well, we know the values of PA and PB. Let's rewrite it in pascals. We also know that PC equals PD, which allows us to write this expression, which becomes this and this, that we'll call expression 1. Let's write it here at the top left so we can't miss it. Now, let's go to the configuration where the points A and B are linked to the manometer. Starting from point A in the direction of B, we write PA plus gamma oil times 1.20 minus 0.90 plus gamma 1 times 0.90 minus 0.30 minus gamma 2 times 1.55 minus 0.30 minus gamma oil times 1.80 minus 1.55 equals PB. Substituting the values, we come to this that we'll call expression 2. Let's bring the expression 1, and here's the system to be solved. We substitute the value of gamma 1 and find successively gamma 2 equals 14,894 newtons per cubic meter and gamma 1 equals 19,362 newtons per cubic meter. There are many types of equipment to measure small pressure differences, but this one is very simple. Its interior is filled with two immiscible liquids of different densities. Of course, the heavier will go to the bottom. The upper part will be filled with the liquid whose pressure difference we wish to know. In this case, we can see that the pressure at the left is greater than the pressure at the right. Knowing the values of H1, H2, gamma 1 and gamma 2, and if we read the height difference delta H after we link the extremities 1 and 2 of the micromanometer to the points whose pressure difference we wish to know, we can write this expression. We know how to do it step by step. And this is the pressure difference between 1 and 2. Now we'll call capital A the cross-section of the upper reservoirs and A the cross-section of the U-tube. We can write this relationship between them. And the expression turns to this. And successively, after some algebraic work, to this final form. P1 minus P2 equals delta H times gamma 2 minus gamma 1 times 1 minus A over capital A minus gamma times A over capital A. Notice that this term is constant for a given system. Now that we've seen the liquid manometers, let's talk a little about the metallic manometers. This is the most popular of them, the Bourdon type manometer, or should we say, the Bourdon gauge, seen by the outside and from the inside. There's a curved pipe known as Bourdon tube. It works like a party blower. It rests when there is no pressure applied to it. When there's a pressure, the tube will extend as it happens in the party blower. But, as we said, there are other types. Here is a shredder gauge resting and submit to a pressure. Now, take a look at this burden gauge. Let's change the position of its pointer. Now, if we apply a negative pressure to the burden tube, it will contract and push the pointer upward. That's how we make a vacuum gauge. Of course, we can set the pointer to an intermediary position and build a Mano-vacuum gauge. Let's make a small change to the burden gauge. Let's close and seal this extremity. Let's do it at the sea level. Now we turn it like this and close it. Inside the sealed pipe, there's the atmospheric pressure, which is equal to the outside pressure. So the pointer is indicating 1 atmosphere. We've just built an aneroid barometer. See how it works. It will indicate 1 atmosphere at sea level, but if we climb a mountain, the outside pressure will be lower. So the pipe will tend to extend, and the pointer will show that the atmospheric pressure has decreased. Torricelli's experiment allows us to measure the atmospheric pressure. We fill the tube with mercury until the top. Then we pour some mercury inside the vessel glass, and there they are, tube and vessel glass containing mercury. Then we close the open extremity of the tube, flip the tube inside the vessel, but don't let the mercury get out of the tube. And even so, the mercury level will go down inside the tube, leaving behind it, what? Nothing but a vacuum. Hey, professor, that's not true. There will be mercury vapor. Okay, you're right. But its pressure will be so small that we'll assume that there is just vacuum, which means that the absolute pressure here will be 0. But we'll talk about this in another video. When this experiment is performed at the sea level in a sunny day, the mercury column will be equal to 760 millimeters. So, this is what we have. Point A, in which the absolute pressure is equal to the atmospheric pressure. Point B, in which the absolute pressure is equal to 0, and the height between them, which is 760 millimeters. The specific weight of the mercury is equal to 136,000 newtons per cubic meter. So, applying Stevens' law to this case, with the substituted numerical values, we find the value of the corresponding atmospheric pressure, 103,360 pascals, or 0.1033 megapascals as you wish. Just for your information, UPAC, which is short for International Union of Pure and Applied Chemistry, has established the standard atmosphere equals to 101,325 pascals. But for our purposes, we say that at the sea level, the absolute atmospheric pressure is equal to 0.1 megapascals, which is equivalent to 10 meters of water column. Okay, that's enough for today. In our next video, we'll talk about the vapor pressures of liquids and solve some exercises about what we've seen until now. See you there! Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.